x is 1. So this is 0. This is 1/3. This is minus 1/5. And this is plus a constant c. So I made this error because when I differentiate this, I get that. But with the 4, of course, I didn't. Okay, so in order to find c, I moved 1/3 to the other side and negative 1/5 to the other side. The least common denominator is 15. I have to multiply negative 4 by 15, multiply negative 1 by 5, and positive 1 by 3. So 4 times 15 is 60 with minus in front, and negative 5, and then plus 3. Negative 5 minus plus 3 is negative 2, negative 62 over 15. So the unique solution, this is the most general antiderivative, but they also ask us to find the unique solution. And I have to replace c by negative 62 over 15. So 3 natural log of the absolute value of x plus x to the third minus x to the fifth over 5 and minus 62 over 15. Thank you. My apologies. Good. Any questions? Any questions? So I was just saying that these are identical. Exactly the same thing. Here the notation is different. So do you feel like doing another problem like this, or can we explain a different notation? It's the same thing. It's the Leibniz notation, but we understand how to work on these, right? We just work on a problem. Let me know if you want us to work on another 21 to 24. If not, we'll move on.
Do 23.
Of course. Let's look at 23. So we have f prime of x equals x to 2/3 minus x, and they are telling us f of 1 is negative 6. So again, nothing new still. This is chapter 4. They're asking us to find the most general antiderivative and also find the unique function that satisfies this condition. What is the condition? Y is negative 6 when x is 1. So then f of x, x to 2/3 plus 1, which is 5/3 over 5/3, minus x squared over 2 plus a constant c. Let's see if we have any questions on this. So we increase the power by 1, and we divide by the resulting number. Is this okay? So this is the most general antiderivative. I will rearrange it and flipping the denominator. So it's 3/5 x to 5/3 minus x squared over 2 plus a constant c. And this is the most general antiderivative. In order to find the constant, I have to use the initial condition, which states the function, not the derivative, right? The function. When the function is negative 6, then x is 1, or vice versa. When x is 1, the function is negative 6. So 3/5 minus 1/2 plus a constant c. I move everything to one side again, negative 6 minus 3/5 and 1/2. The least common denominator is 10. We need a 10, we need a 2, and we need a 5. So negative 60 minus 6 and plus 5. So then the constant is negative 61 divided by 10. So again, this was the most general antiderivative. But now, because we have the constant, we can also determine the unique solution that satisfies the initial condition as well. So f of x equals 3/5 x to 5/3 minus x squared over 2 minus 61 over 10. Is this okay? Is this okay? Any questions? Anybody, any questions here? Before we choose the next problem? Anybody? Okay. Moving on then. On the next page. How do we feel about this? Again, this is just chapter 4 so far. Okay. Now, finally, let's solve. We can work on any of these if you'd like to choose, and then separable equations. Again, this is exactly the same thing, but it's a different outlook. Let's work on 31 through 38, and then we'll come back because you'll see what needs to be done. 31 through 38. Anybody would like to choose? I will choose 31, and then you'll choose the next one. So we have dy over dx equals 5x to the 4th y. So we are moving on to the second type. So the symbol, just chapter 4. The most general antiderivative or the unique function or both. Now finally we're looking at the second situation and the last one in this chapter and sections 5.7. Okay, so as you see, we have in this equation the Leibniz notation. We know that this f prime of x is the same with dy over dx. But the reason why it's not replaced, we have the notation dy over dx is because we have to separate the variables. What does this mean, separate the variables? We want y and any term or factor with y to be on one side. We want x and dx to be on the other side. So here's our first step. I'm going to multiply. I'm just going to copy the equation here. I'm going to multiply by dx. I'm going to multiply both sides of this equation by dx. I need to separate the variables. I'm not there yet, but I definitely don't want a fraction in the equation. So that's my first step. I multiply both sides by dx. Okay, so let's see what happens. When we multiply both sides by dx, we have dy on the left-hand side because dx will simplify. And we have 5x to the 4th y dx on the other. We don't need two equal symbols. Okay, so I am one step closer, but not there yet. What do I mean by not there yet? Well, 5 is okay to be on the right-hand side. X to the 4th is okay to be on the right-hand side. Dx is okay to be on the right-hand side. But y is not okay to be on the right-hand side. So this is okay, this is okay, this is okay. This is not. I want it out of there, but I can't delete it or erase it. What should I do to both sides now to make y disappear from that right-hand side? What do you think we should do?
Would you multiply by y?
You mean divide?
Divide by y.
Yes, we divide both sides by y. So we have dy over y equals 5x to the 4th dx. Now I'm happy. I'm far from solving it, but this is the absolute mandatory step. I managed to separate the variables. Not all differential equations are are solved in this way, only those that we could separate the variables in. So as you see, there is no y on the right hand side, there is only x. And there is no x on the left hand side, there is only y. Okay, of course, what we're going to do next is integrate the left hand side and integrate the right hand side. Okay, so now we have to think. What function prime is 1 over y? And then on the other side, what function prime is 5x to the 4th? But let's start with the left-hand side. What function prime is 1 over y? We had that today. What function prime is 1 over y? It's a special formula, it's a special function, we have to remember it.
Is that the ln, the absolute value of y?
Excellent. 5 is 5, x to the 5th over 5 plus a constant c. I know you're going to ask, and it's a absolutely perfect question, why you integrated the left-hand side and you didn't put a constant, but you integrate the right-hand side and you put the constant? We can put a constant here as C1 and a constant here as C2, but I can move C1 to the other side and get one single constant. That's the reason why when we integrate both sides, we only have one constant. If you feel comfortable, you can put C1 here and then C2 here, but then you move C1 to the other side and you have C. That's the reason why we do not need to use two constants. Good. I simplify. So I get natural log of the absolute value of y equals x to the 5th plus a constant c. This is a huge leap forward, but it's not done. We have to dig deep from chapter 2 when I mentioned the most important, this is algebra. From this point on, there is no calculus. In chapter 2, we said the following. Any log base a of x equals b can be replaced by a raised to b equals x. This is the most important identity in chapter 2. Meaning, what does this mean? Any log equation can be converted into an exponential equation, and vice versa. Any exponential equation can be converted into a log. So that's why we reviewed the correspondence or the conversion, if you want, between a log equation and an exponential equation and vice versa, because we needed it now. We need it now in 5.7. Can anyone tell us what is the base of natural log? I know it's a silly question, but I want to help you use the identity and convert this into an exponential. So we can solve it. We have to solve for y. Can anyone give us the base of natural log? If you look at the graphing calculator, it has to be the same key. I think Shana already showed us. I thought you did. Say it again. Of course.
No.
Absolutely. That's why they are on the same key. Natural log and e to the x are on the same key. So we have the base. So the base raised to this equals the absolute value of y. So e raised to x to the 5th plus a constant c equals the absolute value of y. So therefore, remember the absolute value, so this gives us plus or minus e to x to the 5th plus c. There is a a simpler way of writing this, but I need to remind you of a formula. A to m times a to n. My m has 3 bubbles, my n has 2 bubbles. Copy the base. What happens with the exponents? A to the mth times a to the nth.
And to add them.
Yes. But I can go backwards too. If I have a base raised to a sum, if I have a base raised to a sum, I can go back and write this. So y equals plus or minus e to x to the 5th times e to c. Because this is e to x to the 5th plus c. Why am I doing this exercise? Because this is a constant and it can be replaced by c. If you convert this or you don't, it's okay. But solutions are written like this, plus or minus a constant e to x to the 5th. Because e to a constant is another constant. If you want to put c1, so you differentiate between the two, you can put c1. You can use a different constant. You can use a or b or c, but this is how it is written. Okay, so what was the difficulty with this exercise? So let's start from the beginning and review the steps. I am given a differential equation because it has f prime and the function. So it's a differential equation. It has a derivative and it has the function as well. But f prime is wisely written as dy over dx because this is a step forward in helping us separate the variables. Because I cannot integrate if I have two variables. What is it? Is it dx? Is it dy? What is going on? We cannot. They are double integrals, but it's a totally different story. So I have to separate the variables. What do I do first? I multiply both sides by dx. Okay, dx is gone from the left-hand side, and of course it appears on the right-hand side. I'm happy with 5, with x to the 4th. I'm happy with dx, but I'm not happy with y. It does not belong on the right-hand side. So then I have to simply divide both sides by y. And now I'm able to differentiate. When I differentiate this, I get this. I'm sorry. Now I'm ready to integrate. When I integrate this, I'm getting this. When I integrate this, I'm getting this. Now calculus is done. I only have to solve this equation for y. I know this very important conversion between a log equation and an exponential and vice versa. This says base raised to this equals this. Base raised to x to the 5th plus c equals the absolute value of y. This is what I'm solving for. Now there is another property. Why did I put plus or minus? Because of the absolute value. So the absolute value disappears and then I put plus or minus on the other side. I changed this using this property, the exponential rule. I changed it into this so I can identify this as a constant. And I put it in front. So plus or minus whatever e to x to the 5th. That's why I think this is the most intense type of problem in this class. I think everything else is manageable if you follow my lead. This is a little bit more intense. Solving differential equations. Okay, feel free to choose anything you want. So let's still stick with 31 through 38, and then we're going to look at the last step. Okay, I will choose 33 till you find another one. So 3y squared dy over dx equals 5x. Let's try like we always, contribute even if you're wrong. What do you think we need to do first here in order to separate the variables?
Divide by 3y squared.
No, because I have 3, I have y squared, and I have dy. So these are good.
Multiply dx,
Say it again.
multiply dx,
Multiply both sides by dx. Excellent. Good. So we multiply everything by dx. So here's what we have. 3y squared dy equals 5x dx. Are the variables separated? Because if they are, then I can integrate both sides. If they are not yet separated, then I cannot integrate. X has to be alone on one side, y has to be alone on the other. No mixture.
Yes, they're separated.
They are separated. Now we are ready to integrate. The left-hand side is 3y to the third over 3. Do not put a constant here. We're going to put it on the right-hand side. 5x squared over 2 plus a constant c. There is no need for a constant on both sides, because the constant from the left and the constant from the right will make up another constant. Good. Simplify. So I have y to the third equals 5 halves x squared plus a constant c. It's all algebra now. I need to solve for y. What should I do to both sides to solve for y? That's all I need, and I'm done. Move on.
Where did you get the?
Go
Sorry,
ahead.
Nick, go ahead. You're good.
Go ahead, Will.
Where'd you get the 5 over 2x squared? What was it?
When I differentiate x squared over 2, I get x. I bring 2 down, I simplify, and I get x.
Okay, I see.
Better?
Yeah.
Perfect. How do I solve this equation? What should I do? Again, this is just algebra. Calculus is done.
Just take the cube root. of both
Very
sides.
good. The cube root. That's it. It's done. That's all we need to do. There is no plus or minus on the cube root. So 5 halves x squared plus a constant c. Done. This was easier because I didn't have to solve the equation using the correspondence between a log equation and a exponential equation. It was much easier. I just had to apply the cube root to both sides. Okay. Ready to choose, or I will choose 37. It's up to you. Or even 35. So we have dy over dx equals x over 2y. Everybody's paying attention, so maybe I should have said this all along. It's very difficult, super difficult, and everybody would pay attention. I'm trying to be funny. Okay, what do we do now?
Multiply by y.
We can multiply both sides by y first, but we should always focus on dx, but it's fine. Y is fine. So we have y dy over dx equals x over 2. Okay, excellent. We multiply the left-hand side by y, we multiply the right-hand side by y. Excellent. Then
Multiply by dx.
multiply both sides by dx. Very good. So y dy equals 1/2 x dx. Are the variables completely separated? This is not always possible. There are other techniques in differential equations to solve differential equations there in which we cannot separate the variables. Are they completely separated, or not yet?
Yeah, they're separated.
They are separated. Therefore, the last step of integration, or the last step in calculus. So we have y squared over 2 equals 1/2 x squared over 2. We only use one constant because the constant from the left and the constant from the right make up another constant to put them together. Good. Very good. What should we do now? This is just algebra now. We want to solve for y. What should we do first to both sides? We need to solve for y, but I need to get rid of what?
Multiply by 2.
Very good. So we have y squared equals x squared over 2 plus 2c. Good. Final step. Still algebra, just algebra. We want to solve for y.
Take the square root of both
Very
sides.
good. But this time I have to write plus or minus because it's the square root. So x squared over 2 plus 2c. Done. Very good. Any questions? These are the only three types that you're going to see. A situation in which you take the cube root, a situation in which you take the square root from both sides, and a more complicated situation in which you have to use this relationship between a log equation and an exponential equation. Okay. I would like to also look at one of these problems, because here we are given the initial condition to help us find the constant. So these three examples, we did not have an initial condition. We did not have to solve for c and plug it back in. We were only asked to find the most general antiderivative. But now in 39 through 42, they're also giving us the initial condition. They're helping us find c. Okay, I'll start with 39. If you want to choose the next, please do. So y prime equals 3x plus xy, and they're telling us that y is 5 when x is 0. So this is the initial condition. This is the point they are giving us, 0, 5. Now they're trying to trip us because they are giving us this notation which we have to reject. I reject that notation. Okay, so then what do I replace it with? Because this notation is not doing the right thing for me. Is not helping me solve the equation. So then what do I replace it by? Or replace it with?
Do you have to get back to like regular y after the derivative or before the derivative?
No, just remember, what do I have to do?